Yeah, I think it works. Thank you.
Okay, so let's start now. So today I'm going to present two papers which submit to this year's ICLR about graph structure learning. So actually I think it's a good time to talk about these two papers because last week we also learned some lectures from the news talk about the structure learning problem, and we can learn more about what recent work are concerning about. So the first paper, it is accepted as a poster in this year's ICLR. This paper is called Discrete Graph Structure Learning for Forecasting Multiple Time Series. So essentially, this is a structure learning problem in the field of dynamic graph. So the input signals are of dynamic instead of static node features. So let's first look at the motivation part. So essentially for lots of multivariate time series prediction, the motivation for studying the correlation between different variables has been studied a lot and has been shown that such latent structure uh, can benefit the prediction for many downstream tasks. So essentially exploring of the correlation and causation among the variables in a multivariate time series shows promise in enhancing the performance of a time series model. But in reality, the graph structure is not always available or it may be complete. And because on time series data, if the graph is already known, GNN-based approach show promise in forecasting multi-interrelated time series. So in this paper, they are concerned with structure learning method applicable to the downstream use of GNNs. So one thing to note is that in this paper, although its task is about multi-time series forecasting, the graph structure is assumed to be static across all time steps, meaning that it will only do one-time graph inference and use this static graph to facilitate the forecasting for the whole multivariate time series. So actually, this work is built upon a prior work that Neil has previously briefly mentioned, which is called LDS from ICLR 2019. So in that paper, it proposed to jointly learn the graph structure and the parameters of graph neural networks by approximately solving a bi-level program that learns a discrete probability distribution on the edges of the graph. Note that in the original paper, such structure learning is on static graph, and the problem setting is that it wants to do the usual node classification task on the full graph on some graph dataset benchmarks. However, now the graph structure is not given, so they want to jointly learn the graph structure and also train the parameters within the GNN for message passing in order to get a good prediction for the node classification task. So essentially, uh, in the original paper, they view this uh, structure learning process as well as a neural network learning problem. They form them as a bi-level program, which can be shown as follows. So if we here we only consider unweighted graph, meaning that the entrance of the agency matrix is either 0 or 1. And the idea is that if we assume W is the parameters used in GNN, and also we assume that each of the entrants within this agency matrix is associated with a binary follows a binary distribution parameter by this data. So we also have the node classification loss on training dataset and the validation dataset. The idea is that I'm going to try to minimize the error, which minimize the node prediction uh, uh, error on the validation set. And in the meanwhile, this GNN structure would the parameters of the GNN would be the selection, would be the one that minimum the classification error on the training data set. So through this bi-level program, we can actually optimize this set of two parameters, which is theta and W iteratively, because essentially we can view this theta as an outer optimization parameter, and this W, where this W is an inner optimization problem. So the
Yes.
idea is that maybe we can firstly do the sampling of theta to get a fixed A here, and once we get a fixed graph structure, which is A, then this W is just a normal GNN parameter learning program on a given graph structure. So essentially, the optimization will trying to iterative over these two parameters. And here's an illustration of possibly how the whole process is going on. So essentially, given the original data points, we are going to do firstly initialize the parameters for GNN and the graph generator. Hello? Uh, Hi, Wei, can you still hear me?
More.
Hello, is my audio has some
Zijie can
faint
hear
right now?
you.
Okay. Um, okay, so maybe let's continue. I do not know whether is it some technical problem here.
Hello, Wei, can you hear us? How about everyone else? Can you hear clearly? Maybe
I
just
can hear.
okay, good. Thank you. Yeah, I think we are good.
Okay, sure. So, give me a second. Okay, so essentially, the whole procedures goes like this. So for this graph generator, essentially this is a also like this theta where each theta ij is for the Bernoulli distribution for each of the entrants. So it's also an n by n matrix, and also we have the parameters for the GN. So essentially, we first, for example, assume that this graph is connected via the uh, uh, KNN, for example. So we can do a initialization for this data. And then based on this initialization of the data, we're going to generate several sampled agency metrics, which is A1, A2 until A tau. And for each of these generated graph structure, we are able to get this updated. We are going to use this graph structure sequentially to update this W, because once we already have this graph structure, it's going to be an optimization problem where this GN is operated on a structure that is already known. So essentially, we are going to update this W several times. And once we update this W, so remember that the outer loss is can be back propagated while the node classification loss on the validation set. So essentially, we can do the back propagation through the hypergradients update, which is just the uh, following the chain rule. So essentially, it will go through this W to update our data as well. And these procedures will go iteratively until that the changes of these two parameters is below a threshold. So uh, so here is so this is the prior work that this paper is built upon. However, for the current solutions, there are mainly two drawbacks. Firstly, the computation is expensive. This is mainly because that the when we want to do the backpropagation of W with regard to theta, it is equivalent to differentiating an RNN, because we remember that each of these W is get updated by a sequence of sampled graphs. And secondly, if we look at the number of parameters, of course, for GNN, this W is always what we want to learn. But for the graph structure learning part, we assume that this theta is an n by n matrix, and all these n by n entries are all free variables that we need to optimize over. So essentially, when this number of nodes gets larger, that means that we have n square entries to be optimized, which may be hard to scale when we deal with many large graphs. So why we would why so essentially in this paper they want to propose a more efficient way to deal with the joint learning of the graph structure. So instead of formulating it as a bi-level optimization problem, they just view it as a unilevel optimization, where they assume that now this theta is no longer an n by n matrix where all these n by n entries are learnable parameters and need to be optimized. Instead, this theta, this is computed from this W instead of treated as free parameters to be learned. And we will talk about the details of how we are going to generate theta based on this W, and uh, that is basically the core design of this paper. And once we have this unit level optimization, back to our current problem setting, there's another thing different from the original paper, is that this one is based on the uh, time series data. So essentially the training procedure would be a little bit different. So the difference is that if you think about the static graph fitting, it's just you need to utilize the node features at just that static graph to do the inference. But now, since we have the node features at different time steps, we are going to kind of use a sequence of node features to firstly infer what the graph structure looks like, and then make the predictions in the following timestamps. So essentially, the training loss is by viewing this model as a sequence to sequence model, where the model F is trying to trying to make predictions on the node features in timestamp t plus 1 to t plus capital T, and the error is just the predicted value to the ground truth value. Okay, so here's an illustration of the proposed method. So assume we have four coupled time series, and we are going to kind of use a window data, and such window data is what's the first part, which basically is what we have observed, and we want to, based on this observed one, to make predictions in the following. So based on this observed sequence of data, we're going to do the feature extraction, where we try to extract each of the four theories as a vector. So denoted here. Here we generate four vectors based on this four sequence, and then we are going to and then they are going to use this four vector to go through a link predictor in order to get the node structure. And finally, based on this data, because remember we also assume that this theta is just a Bernoulli parameter for the sampling of each of these entries. So we are going to the sampling to get the sample graph A. And once we get this graph, and also we assume that this graph is static across all timestamps, and then this problem just becomes a novel multivariate time series prediction with known graph structure. And that can be done in many proposed method. For example, and these methods are mainly recurrent graph convolution. So essentially, it's just a variation of RNN, where RNN just deal with one time series, but recurrent graph convolution may deal with several time series with known graph structure. Okay, so now let's look at what they have proposed to calculate this theta directly from this W. So essentially, actually, I'm going to talk about it later. It's very similar to another paper that I have previously talked about, which is neural relational inference. But I think this paper have formulated the problem in a more different way, and we will see. So essentially, as we see that now this theta is no longer initialized as n by n free parameters. Instead, they are computed from a neural network, which is called a link predictor. So essentially, once we obtained the feature vectors for each of the time series, which is this Zi and Zj, then each of these corresponding entries between this I and J will be computed via, for example, very simple neural networks like the MLP. Instead of, and the final output will be go through a sigmoid function, so that each of the data will be within 0 and 1. So here we can already see the difference between the previous approach to this approach. And the thing is that in the previous approach, all of these n by n theta, they are all free parameters. So we'll have n by n parameters for learning graph structure. But now, if we're trying to generate this theta instead of viewing it as all learnable parameters, then our parameters are just these two, for example, these two layers of MLP. So the number of parameters can be reduced and can be controlled when we deal with different sides of the graph. But one thing remaining here is that once we computed this theta in this way, now that this, but in our previous assumption, the original graph agency matrix A is discrete, meaning that the entrance is either 0 and 1. So we need to play a trick in order to do the backpropagation to the graph, to the link predictor network, which is this two fully connected layer. So the trick is what we probably already know is by using the Gumbel reparameterization trick for discrete sampling. So essentially, we need to compute each of these entries of Aij by utilize this Gumbel reparameterization. And once we did that, we can do the like backpropagation to this fully connected layers easily. And
So can you elaborate more? Because I think everyone is more familiar with the reparameterization trick for the continuous case, right? For the Gaussian distribution. But then for the discrete case, actually this is my first time to see. Actually, we can do the similar trick in the discrete case. So can you elaborate how we can exactly do this and why this is a reasonable reparameterization?
The idea is that because now this theta here, we view it, each of these theta ij here, it is a continuous, it is a continuous variable, right? It is between 0 and 1. But this aij, we assume here, it is a discrete variable. And each of these, the aij should be sampled from the Bernoulli distribution parameterized by this theta ij. So this Gumbel reparameterization trick is used for do the backpropagation when we're trying to sample this discrete variable Aij from this theta ij.
Yeah, I understand the motivation, but for the exact trick, because in the Gaussian case, we just sample from a standard Gaussian distribution, and then we can just do some scaling with the sigma, and then do a shift with mu, and then we can guarantee that, okay, after we sample that from that standard normal distribution, and then we do that rescaling and shift then the output is guaranteed to follow this Gaussian distribution with mu and sigma square, which are the output from some neural network. So here, I just want to understand what are the details. So, for example, you're saying GIJ1 and GIJ2, what are they? And when we say it's sampled from this Gumbel distribution, what does that mean? What's the Yes, I just want to know the details of this part.
Also, essentially, you want me to explain the kind of the math between Gumbel reparameterization trick?
Yeah, I don't know how hard it is because for the Gaussian one, it's quite natural for everyone to understand. I just wonder whether this part is also very natural.
I currently I think because this Gumbel reparameterization trick is proposed, I think in 2016, if I remember it correctly, and that derivation is kind of a whole paper, but I do not know whether anyone here has a clean idea to explain what's the to explain it very concisely what the math is behind it. If but for me, I don't think we can. I I I currently am
It's
not
okay,
able
yeah.
to summarize it very clearly in just several sentences. But do you think it is a good idea that I list the corresponding paper later on after our discussion today?
Yeah, it's good because I just wonder whether it can be explained in a very simple way. If it's like requires a couple of pages to prove, then definitely, yeah. Just give us the link and probably can read later. But at least do you know what like from the implementation purpose, do you know what will be the output for this GIJ? So is that just 0, 1? And what is that as? Do you have any idea for that as well?
So this S essentially it is called the temperature. So
Okay.
essentially, from the paper, it has proved that if this S is approaching zero, then this theta ij would then if we computed this aij from this formula, then the probability of aij of being one is close to theta ij, the value itself.
I see. So I try to provide my explanation here. So this GIJ, GIJ1 or GIJ2, although I do not know exactly what they are, but they are random variables. They push the randomness, the need to sample some like discrete variable from the Bernoulli distribution with theta into the current situation. They kind of sample random variables from this Gumbel distribution that will be served as additional input. And then together with the first term, which involves this theta ij, right, so which is the output of a neural network. Then with this formula, then we can approximate. I'm not sure whether it's exact or approximate, but this aij should follows the Bernoulli distribution with parameter theta ij. But somehow we avoid try to directly sample from this Bernoulli distribution with theta ij because it's kind of make the whole process not differentiable. Right? But right now, it's just say, oh, it's a function with theta ij and some like random variable sample from a given distribution. So everything is kind of still kind of can be back propagated, right?
Yeah, and I think through the implementation wise, one thing is that although we see that when only the S is approaching the arrow, this aij, the probability of it to be one is proportional to this theta ij. So, but doing the implementation, usually we will first doing each iteration, we will kind of decrease this as one iteration by one iteration instead of just setting it.
I see.
Yeah. So
Is
that's
it
just
similar to the softmax, Gumbel softmax? So it's like
yes.
the output from the Gumbel distribution is this GIJ1 or GIJ2. They are just 0, 1. Is that the case?
Yeah, so Gumball softmax is a case where that we have, for example, the output label is not only 0 and 1, it can be multiple class. But here you can see each of these AIJ can just be 0 and 1. So we no longer need Gumball softmax. Instead we just use this output function, use this mode instead of softmax.
Okay.
Okay. Yeah, I will send the corresponding paper link after the discussion. So essentially from this trick, we are able to do the backpropagation through the from this link predictor. And in this way, we may have fewer parameters compared to we totally let this theta to be nullable matrix. So another thing is that besides this, they have ended a regularization through injecting a prior knowledge of the pairwise interaction. So generally, they see that even if an explicit structure is unknown, a neighborhood structure such as a KN graph may still serve as a reasonable knowledge. And sometimes the underlying graph is known, but may not be the optimal one for GNN to make prediction. And this can also be served, but we still do not want to waste such of signal. So here they proposed of ending them as a regularization to guide the knurling of the structure. And here I want to like emphasize one thing through kind of this graph structure knurling problem. So essentially, the graph structure knurling for example, when it is considered with different downstream tasks, like in the static graph, maybe node classification, in the multivariate time series, it may be forecasting tasks, the node graph structure may not be the same. The optimal graph structure may not be the one as a ground truth graph structure, because here our goal is to maximize the performance of the downstream task, and the graph that a GN can make the best use of may not be the underlying ground truth graph, and it is usually the case. So essentially, if the graph structure knowing problem can be meaningful even if the graph structure is already known in many cases. Okay, so essentially, okay, so here I have another example for saying that. So previously, also read another paper published in CVPR, and the problem is that they have a people walking, and the skeleton of a walking people can be viewed as a graph, and each of the node within the graph is just its joint. And the task, for example, is to do the person's action recognition. And in order to do the action recognition, you need to uh, uh, kind of infer an underlying graph where the graph has connected two joints, which is not naturally connected in your skeleton. For example, when you are waving your hands or something, you might connect your joint on your hand to your joint on your elbow or something like that. So essentially, there's not many other papers where, although there's a given graph already, they also do some graph structure inference. So here they propose to end such regularization through and they call it, of course, a prior, by injecting it into this loss function. And essentially we can see it's just the cross entropy loss between the prior knowledge, which is this AIJ we already know, and this theta IJ that we've learned from our neural network. And the overall training loss is then the basic forecasting loss, where you see that we want to forecast sequence. So essentially, it's a summation over all the timestamps that we want to predict, and then plus a lambda multiplied by this regularization loss. And after I read this paper, I personally feel that this is very like what previously I've seen in the neural relational inference paper in ICML 2018. And the author also discussed about the differences between these two. So in the original NRI paper, actually, it is it is also studying exactly the same problem. We are given a multivariate time series. They want to make predictions, but they know that there's some underlying structure among these different variables, but they do not know what the structure looks like. So essentially, they proposed a latent variable framework, which is following the structure of VAE, where their encoder is just similarly trying to use a sequence, a window size of all this data they've observed so far to infer what is a corresponding uh, graph structure. Uh, Similarly, they will model it as a distribution and then pull from it, and the decoder is just like what the here what this recurrent graph neural network doing is just that knowing that graph structure, I'm going to utilize this graph structure to make the prediction. So this paper talk about that they claim the most essential distinction from this approach to this NRI is that the number of structures. So they see that if we view theta as the structure and each of this graph A that sampled from it as a graph because they are combinational remaining graph samples from the same structure, they claim that this approach produce one single structure given one set of n series. On the contrary, the NRI paper just produce different structures given different encoding inputs. So a feasible use of NRI can only occur in the following two manners. The first one is that a set of n series is given and training is done on window data, where each window will produce a separate structure. And secondly, many sets are given and training is done through iterating each set, which corresponds to a separate structure. And so for this one, maybe it may seems not very clear to you. Let me rephrase it. So if you look at here, this problem setting, essentially this proposed model is used when is essentially used for transductive setting, where it's just trying to, whenever it comes a new time series, it will uh, it will trying to infer the corresponding structure based on that only based on that input data, but it will not make some assumption about that the the commonness between different samples. But the training structure of the NRI is that they are trying to because it is following the VAE structure and there's a prior assumption put upon this each of these inferred edges, and that is shared among all the inferred structures, and they kind of assume a common sense structure among uh, all the different systems. So in other words, NRI may not scale very well when there's when in the transductive setting, whereas this model it may be more reasonable when we just want to do the inference over just one system. And the second thing is that the H prior in NRI, if we look at the loss, is just the KL divergence loss between the inferred edges and the prior on the edges. And the prior on the edges is just like many other VAE model is assumed to be Gaussian, which is just assumed that uniformly sampled from 0 and 1. But here, if you look at the prior knowledge that it imposed through the loss function, it can be any kinds of prior, because this Aij can be any value. So it can have some structural information here. So that's the two major difference it claims from the original NRI paper. And so here is their experiment results. So essentially, they've compared with many traditional time series model like ARIMA and also some deep learning based model. So essentially, they are able to have superior performance over all these baselines. And one thing I want to show here is that they also claimed that they also compared the training time for their model. And yeah, so here is the training time on 3 different data sets. They compare the performance for this, this is their model. This is, the blue one is a model with known graph structure, meaning that this one is just to do the prediction when the graph structure is given. And this one is to do the prediction without any known structure, but the theta itself is viewed as an n by n free parameter matrix, as we discussed in the first related work. So you see that once we generate this data, instead of viewing this data as all parameters, all free parameters to optimize over, the time the time for training can be saved. So you can see if we view all these parameters in this data, if we view this data as a totally learnable parameter, the time for training the model would be very, very large. And another thing to notice is that if you compare the blue one with the green one, approximately the time for doing the prediction when graph structure is not known is about 3 times greater than the one where we already know the graph structure. So essentially, we can see that do the graph structure learning kind of is sometimes the efficiency for doing this graph structure learning can really play a very big role, because compare that we already know the structure or we do not know structure for the same prediction task, it already be 3 times higher than the original approach. Not to mention if we do not decide the graph inference procedure very properly, the time the efficiency of the algorithm might be a very large problem. And they also studied the influence of varying k, and also varying of the regularization weight for this prior graph structure knowledge. So here we can see that using a smaller k or increasing the regularization magnitude will produce sparser graphs, which is what we have expected, because essentially when we're using this smaller k, we're assuming that the prior of the graph is that the nodes are not connected. Each node is not connected to many nodes. So the graph is essentially sparse. And another thing is that by varying these k and lambda, the mean absolute errors are all around the same magnitude, indicating the equally good forecasting quality compared to other baselines. And finally, they studied what is exactly the node graph. So essentially, as what I have previously mentioned, the node graph is not necessarily to be the ground truth graph, because that may not be the best graph structure to be utilized by GNN. So here the measure how far the node structure differs from the given agency matrix by using the regularization loss divided by n squared, because the regularization loss is the cross entropy loss for each of these entry, ground truth entry to this predicted entry. And there are n square entries, so they divided it by n square. So here you can see that, so here is the results. Essentially, if the lambda is relatively small, or in a very extreme case, lambda equals to 0, meaning that the graph is with no any prior knowledge and can be nulled very frequently, then the okay, they didn't put the results here, but the results for that kind of nulling would not be so good without any like of this supervision. But when this regularization term gets larger, the error will also raise, because it will pose the model to NER a structure that very like the ground truth graph, but the ground truth graph may not always be the optimal one. And here is the one of the optimal graph that NERD from their model, and the black lines are the original structures contained in the ground truth graph, and the orange dented lines are the new edges that the model have NERD by itself. And through experiment, they found that such graph structure in the traffic network prediction problem can perform better.
Yeah, I want to make a comment here. So I think I really like the idea that they don't think there's a ground truth graph, and I agree with that. So I think the observed graph, it has this discrete structure, and we really should consider it's just a sample from some sort of distribution, right? So
Yes.
it's like it contains noise and it has this uncertainty. So I think the idea to consider it is sampled from some underlying structure and the observations discrete, but we can only partially trust this observed structure. But the underlying this theta is something that we really wanted to explore. And the second thing I think it's very important is like I think this paper tries to sample this discrete graph from that underlying continuous theta structure, right?
Yes.
So I think this uh, can of course like it was like in terms of parameterization, I think the current theta is already more efficient than the full uh, parameterization, which means I treat each theta ij as a separate parameter. But
Yes.
other than that, the sampling process will give us the flexibility to go back to some discrete structure. So then that will make the graph neural network computation much faster, because theoretically we should be able to just utilize that theta structure to do the graph neural network propagation, right?
Yes.
But they didn't do that because they know that it's going to be too time consuming. Instead, we can just sample some discrete structure. And then based on that, then we can already kind of do the prediction. But yeah, by the way, it's a related question to the second comment. How many samples they need to make?
Are you saying how they can compute this?
They are going to sample this A from that theta, right? They're going to sample a bunch of them, and based on each discrete structure, they can do the graph neural network computation. And I guess they are going to do the average to serve the purpose in the end.
Oh, so essentially, here so essentially this sampling, because now it is conducted on the transductive setting. So essentially, there's only one structure for this, one structure for the whole time series. So essentially, they are going to sample it. I didn't say it's implementation, but I think this sampling is because the sampling is also adopted in the original NRI paper. And in this NRI implementation, they sampled it 3 times for each of these data to generate this AIJ.
I see.
Yeah, and then they will do the error is just the average of them.
Yeah. I think this sampling is like try to make this graph this real discrete. So of course, like if we sample different times, then the observed graph will be different, but somehow it will not affect the final prediction that much. Right? Of course, it's more interesting to predict the distribution, like in terms of error, in terms of other things. Like if we sample the graph, let's say 100 times, what would the error distribution look like? That also would be very interesting.
Yeah.
But
Please go ahead.
yeah, somehow I think it's related to your current research, right? So we were thinking about how we can generate a discrete graph. Probably this can provide some insights. Yeah.
Yeah. And yeah, so that's essentially the difference. That's essentially all the like methods and experiments from this paper. And through this paper, I think we can learn something. The first thing is that if you see if we look at the graph structure learning part, essentially this paper assumes that is built upon a prior work, and compare the prior work with this work is that there are kind of two popular methods for learning this graph structure. Easy way direct standing at the parameter size. So one is that we directly optimize each entrance in A, and the second is that we learn the link predictor, which is a neural network, and generate this A from all these node features. And however, although we see that directly optimize A will have more parameters and maybe use link predictor, it can be more parameter efficient. There's also some problems here. So using a link predictor, so for example, the two layers of MLP we've just set off, it also needs to calculate the pairwise node similarity, which the computation will take O(n)² times. And why I raise this question is that if we consider the graph itself is evolving, the problem will become more challenging. So we will not only, if we go back to the training time for each epoch, so here the training time for each epoch is just that because the graph structure is assumed to be constant across all the t time steps, uh, here. So essentially for all this t, we only do the inference for graph structure once. And the time consumption is already larger than we, 3 times larger than the one we already know the graph structure. But if we consume that all of this t times the graph structure will not be the same, which is also very natural in many cases, the time consumption will be much larger. So essentially, I believe still the efficiency for doing this kind of inference of this latent graph structure can be a very important challenging problem to solve. And also, when the graph itself is evolving, not only the computational wise problem we need to solve, another thing is that as the another paper that Zenil has mentioned last week from Eric Shin's group, it also considered that the consecutive graphs generated across adjacent time steps may have some shared constraints. For example, this generated graph across timestamps across a very small time window may need to be relatively smooth. So such kind of constraints, I think, currently are not addressed in this neural-based approach. For example, for this NRI paper and for this paper, if they want to generalize it when the graph structure is not static but also dynamic, then they are going to just use this graph every time at each time step t. But there's no constraints on making some made on some there are no constraints on the generated graphs across different timestamps. But that one has been addressed in some previous approach that is purely optimization-based approach. And this optimization-based approach is from the first category, where this A is just nerd parameters, all nerd parameters. So essentially, I think neural-based approach currently have not addressed this issue yet from the paper that I've read so far. And yeah.
So if we agree that actually the link is largely determined by the latent node features, so then we actually can put a constraint saying that the latent representation for each node across different time, especially across ages of time, should be close to each other. And somehow this kind of smoothness among consecutive graphs at the edge level should also be kept. So we can probably just kind of convert this edge-based constraints into this node-based constraints. So that would be much easier. And also, and also related to the second item here, right? So indeed, it's very expensive to really calculate the pairwise node similarity. So in other words, the theta ij is determined by the although it's a function of like Zi,
Yes.
Zj, but it's still we need to go through every
Yes.
pair. But then if we look at the formula here, right? So we know that if Zi and Zj, they are on like based on yeah, there are different options, but suppose we're based on dot product to decide that theta ij, then we know that for Zi and Zj, if they are not that close to each other, then theta ij is going to be very tiny. If the probability is tiny, then it's almost unlikely that we're going to sample a positive link for that particular theta ij. So that's why we can also build some sort of index just at the node level, right? So for this Zi, we just need to look at this bunch of j, and then we want to compute that theta ij. But for the remaining parts, we just assume them as 0. So in this way, we were not going to make too many mistakes. Right? So somehow we can also use like index to reduce the time complexity.
Yeah. And the second paper I'm going to introduce is just
can I ask a question?
Okay, sure.
Yeah, just before we move to the second paper, also follow up on what Yizhou just commented. So to me, it seems like this regularization based on the ground truth graph edges is very important for the whole framework. This is just my intuitive understanding. Because if we think about the case where there is no ground truth edges, like all the nodes are disconnected at the beginning, and then like Yizhou just said, probably when we determine the theta, we consider the dot product between two node embeddings. Then I was thinking in that case, if two nodes started with very simple raw features, then it's very likely we will create an edge between them. But after we create edges between these very similar nodes, then the message passing will also like exchange information between them, make them like even similar. So I'm thinking about whether this will end up with the case that similar nodes formed into different connected components, but non-similar nodes never get a chance to be connected together. I was wondering if no edge information is known at the very beginning, then we may get some like unrealistic graph structure like what I just described.
Yeah, so I think that's a very good comment. So in other words, we still need to have some sort of guidance, right? That's why they have put that regularization term. And if we look at that, we can, although it's written in a way as cross entropy, but also we can consider it's like we try to maximize the likelihood that this ground truth graph can be observed with a high probability, right? Yeah. So and also here I want to point out that we have a time series. So I think the Shitang, the situation you have just described probably is less likely to happen. But if we do not have this rich dynamic information, if we just it's like we don't have like very good like feature, and the feature somehow is determined by the structure, and the structure is determined by the feature, then indeed it's very likely that we just randomly group things into disconnect components, and then they will become similar because they're connected, and then they will never break the kind of structure that just happened by chance, right?
Yeah, I have no more questions. Yeah, thank you for the explanation.
Okay, yeah, so actually I think what we have discussed here regarding this previously regarding this second bullet point is that we kind of for example want to save the computational cost of this pairwise node computation by using some index, and that's what have been discussed in the second paper. So the second paper is another submission to ICLR 2021, but it has not be accepted yet. But I still think the idea-wise or the methodology-wise is quite interesting. So this one is kind of this one is self-supervision improves structure learning for graph neural networks. So the setting, overall, this model will tackle the problem where it use some KNN-based method kind of do the first grouping of the nodes to save the time for the computation of this O(n) square times O(n) square. And secondly, they see that if we want to do the node classification task without knowing the graph structure on the graph benchmarks, then the label for these graph benchmarks may not be enough for the model to both learn a good prediction for node labels and also learn the structure. So essentially, the idea is to add another self-supervised task to facilitate the learning for both graph structure and the GN for node classification. Yeah, so that's basically the motivation here. So essentially, the number of possible graph structures grows exponentially with the number of nodes, and obtaining node labels is typically costly. The number of available labels may not be enough for learning both the GN parameters and I-agency metrics, especially for semi-supervised node classification. And they propose to supplement the classification task with a self-supervised task that helps learn a high-quality agency matrix. Specifically, it masks some input features and trains a separate GNN, aiming at updating the agency matrix in such a way that it can recover the masked features. So here's an overview of the proposed method. So given so here this paper is just is doing the graph structure learning on static graph. So essentially, given a set of node features, they are first going to use a graph generator to generate a agency matrix, and such generated agency matrix may not be symmetric and may not be normalized, so they will pass it through an agency processor, which is not very important in this model. And this agency processor will make the generated graph to be symmetric and normalized. And then we have the both the node feature and the node graph. So we just do what we usually do to send them all into the GN to do the node classification task. And the second branch here is that we want to end it a self-supervised task, because now the label we have only because currently the label we have are only for node classification. It may not be enough for learning both the generator and also the GNN for classification. So it will firstly add some noise to the original node features, and again, they are going to have a second GNN. So that second GNN is trying to, based on the input noisy features and the generated graph, trying to recover the original features, that is to denoise these features, to make this one to be as close as the original features. So that's essentially the overall framework. We're going to look at each of these components in detail. So firstly, one important part here is, of course, the graph generator. So again, they also proposed these two kinds of approach we've already seen so far. The first one is that, okay, all these agency metrics is just one free parameters to optimize. And of course, in their experiment, once we view this A as a free learnable parameter, it gives this model so much flexibility, and given such limited labels, it may not have very good performance. And the second method is what we see in the previous paper. Is based on it's just based on the inferring the graph structure from the node features, for example, the MLP of X. But different from the previous approach where it needs to compute all pairwise node interaction. Here they were going to combine the KN methods with this MLP. So essentially, compare with existing learnable graph generators, it will not do the computation over all pairs of nodes. Instead, once generate the graph structure, it can compute the edge weight on those existing edges only. So that means that, okay, we first send this initial node feature by transverse it to a hyperplace, for example, through an MLP, and then we're going to use KNNs to generate to extract, for example, the k nearest neighbors for each node, and we'll assume the structures are only exist in this kn-based neighborhood structure, and that will reduce our number of links from n squared to a smaller number, right? And then after that, we're going to compute the corresponding edge weight based on this KN generated structure, and that structure can be computed again based on some, for example, a basic neural network that is a similarity neural network. So in this way, it's kind of it's kind of reduce the computational cost for inferring the graph structure, and
sorry,
also
I have one question. So,
okay.
So for doing the KNN operation, it's still ON squared, right?
Oh, so essentially in their implementation, because for KN there are many advanced way to do the KN. For example, KD tree, and also use some hash tables. It can be not n squared, right?
So KNN means for each node I consider the K closest neighbor to me, right?
Yes.
Okay, and then
yeah.
And then I think just like to my understanding, because they think later on when they do the say like the link the adjacency matrix computation or whatever, they don't want to consider all pairwise relationships, so they choose to first consider only the KNN neighbors. But I'm thinking that at this stage, when we do the KNN computation, it's also n squared.
Why
so
is
a lot
KN
of
squared?
tricks.
I think yeah, if you do it right, it should be lower than squared, right? Because with index,
Yes.
it's it could get down to like n log n time.
Oh,
Yes.
okay.
Yeah, I think that's a very good point, because if we just do the original KN, it is just we still need to go over pairwise computation. But since KN is have been well studied, so there are many advanced methods, which, for example, KD tree and also many others, it can reduce the computation cost very largely. So this may help combining this KN with this method, it can reduce the computational cost.
Yes, I just want to mention a very interesting method called random projection. So suppose we have d-dimensional vectors in the space, and then we just want to generate maybe another like 100 lines, but then according to whether it's on the positive side or negative side of that line, so then this vector can be turned into like 100 dimensional Hamming code. So if we have Hamming code, we know that then we can just build this hash index, right? This kind of hash index. So we can, in a constant time, try to decide which other vectors actually have the same binary code as the current node. So that will be super fast.
Okay, yeah, thanks. Yeah, I see maybe one message from the chat. Oh yeah, thanks Zinil. So Zinil has pointed out that method which can be very fast compute the similarity search. Okay, yeah, so essentially we can instead of using neural network to compute the pairwise similarity, which is essentially needs to take ON square, because the neural network we decide is must take the input of two corresponding nodes and then generate corresponding edge features. But there are many other methods which can firstly kind of do, the idea is just to do the projection maybe of the nodes and then group them so that the search space of the pairs of nodes can be much smaller. So this can maybe accelerate our algorithm. And once, so that's essentially in this paper, they just adopted the KNN to do kind of this pre-processing of nodes and then to infer the corresponding edges only on these selected node pairs. And one thing they show that from their empirical study, the initialization of the graph generator is important. So one good choice thing is that is to initialize the graph generator so that the generated graph before training is the agency matrix created by applying a KN function on the initial node features. So essentially, if we consider this, so if we consider the graph generator, it's essentially once we selected pairs of nodes, we were going to generate the weight for each of these names, and through the KNN, actually we are able to, or the other similarity methods, we are able to get the pairwise similarity on the selected pairs of nodes. And they claim that a good initialization is to initialize the graph generator parameters so that before training, the parameter can already output the desired age weight compared to the output algorithm, for example, of the similarity calculator, like the GN in their case. But they also try to initialize it just randomly, but and it will also outperforms other baselines, but just a simple trick that they shown in their experiment, that such initialization may further enhance their performance. And the second important part is how they end the self-supervision. Now that we have already know how the first pass goes, and now the second thing is how they end their supervision for generating more nodes, for more signals, because now the network not only needs to know how to do the message propagation, but also need to know how to infer a graph structure. So the networks must be more complex and needs more supervision. So the idea is to train a denoising autoencoder, which tries to recover original node features from noisy node input. So you can see the loss is from, so essentially they are going to do a selection on some of the nodes to make them noisy. And through this noisy node, they are trying to minimize the loss from the original input feature and the denoised feature from this denoised GNN. And this denoised GNN will take the input of the noisy node features and infer the graph structure from the graph generator. And the way they are going to end the noise, if it is a binary feature, they will just select this IDX nodes and ranked some percentage of them to 1 and the remaining some percentage of them to 0. And this procedure will be conducted at every training epochs. So at every training epochs, the noised node features will be different. And if it is a continuous feature, it can either replacing the values at this index with zeros or by adding independent Gaussian noise to each of these features. And they here provided an example showing that it is very necessary to end such self-supervision. So essentially in the original structures and train validation test splits of the benchmarks, around 80% and 89% of the nodes and are not connected to any enabled or trained nodes. So essentially, if So essentially, with the self-supervised task, although these edges may not receive supervision from the min task, where the min task denotes the node classification task, the supervision provided by the self-supervised task helps learn and approximate weight for them. So here is an illustration. So if we would look at these two kind of nodes, let's assume we use let's use 2-layer of GNN, then the edges then there will be no supervision between the edges of these two unlabeled nodes, and because now we're currently not only interested in learning these labels for this node, but also learning the possible edge weight or edge structures between pairs of nodes. So if we only utilize labels for this node classification task, then it may not be sufficient. But from this self-supervised task, we will try to denoise some of the original node features. So it may end the supervision for these edges, which may benefit the learning for both graph structure and the node downstream task. And of course, the training is considered by the combination of the two corresponding laws. The first loss is the downstream task loss for, in this case, which is the node classification. And the second one is for the loss from the self-supervised task, which is from the denoising task. And we ended at lambda to adjust their corresponding importance. And here's the relationship. Here's the results for them. So these results are the node classification performance with no underlying graph input. So they have compared with simple MLP-based method, and also from the LDS one we have just talked about in our first paper. And through their experiment, they are able to achieve great results, mostly in this MLPD structure, meaning that they firstly will conducted this KNN, and the graph initialization is the initialization of the graph neural network is to assume to be output the same or similar one as what the KNN outputs. And also they verified the effectiveness of the self-supervised task. So they constructed a variance of their model where the agency matrix is not only based on their self-supervision task, and the node labels are only used for early start. So meaning that they firstly only utilized this branch without this later two, because here essentially is the node classification task. They first use this branch to learn the graph structure, and once they get this graph structure, they fix it to train the parameters of this one. So essentially, this is what we have got here. So you see, so here is the results for its original model, and this is a model that the structure is only trained on self-supervised task, and this is the performance of just using this KN-based GCN, meaning that the graph structure is not nerd, but is just to assume that the latent graph structures is obtained from a KNN output. So both the proposed method and also the variance of them can surpass the KN-based baseline, where the graph structure is assumed to be fixed and not learnable, and the performance of this agency matrix that is not only from self-supervision task without utilizing the node labels can already surpass this KN-based GCN baseline. So verifies the effectiveness of the self-supervised task. And they also studied some parameter, for example, the influence of lambda and how to select this K. So essentially, actually for different graph generator, they have different sensitivity to the selection of K. For example, if it is the for example, if the graph generator is assumed to be just a one theta, the K only affects the initialization of the theta agency matrix. So you can see this red line is not very sensitive to the change of this K. But for the blue one and this green one, where this KN will going to firstly be used to select the pair of nodes, so that they will definitely affect more for this kind of graph generator. So you can see they are more sensitive to it. And for large values of K, the extra flexibility of the MLP generator enables removing some of the unwanted edges. So you can see here in all the experiments on the graph benchmarks, the MLP-based generator or the MLP with KN initialization-based generator can be performs the best. But if we assume if we push this K to very, very large, we basically select all pairs of nodes to be taken into consideration, then this MP-based generator will, because it will not utilize KN to do any selection, so the flexibility of it will allow it to somehow surpass the performance of MLP-based and MLPD-based, because these two will select edges based on KN, and this KN will assume very, very dense graph when this K gets larger. And the node graph, they also, as what we've talked about before, does not necessarily resemble the original structures, but they analyzed how they did analyze what the node graphs look like. So essentially, the x-axis is a range of different pairs of the age weight, and the y-axis is the probability, or here it is the odds that two nodes connected while this age weight will share the same node neighbors. So you can see when this age weight gets larger, the nodes that connected by this kind of age is more likely to share the same neighbors. So that's essentially the second paper that I've introduced. So essentially, it proposed another way which may for the graph generator, which may be more efficient to compute the latent graph structure. And secondly, due to the limited node neighbors problem, it ended a self-supervised task for better guidance. Yeah, so that's essentially the second paper. And finally, I want to make some comments on the graph structure learning in different settings, because essentially from many papers that I've read so far, I think the settings for graph structure learning can be very, very different. And all of them have different challenges to be addressed. So for example, there can be static graph structure learning, which is exactly the two papers we are talking about, meaning that we only infer one graph structure, no matter it is from dynamic signals or it is from static signals. And the second category is just the dynamic graph structure learning, where the graph itself will evolve and the node attributes will also evolve. And through this kind of category, as I said, that the computation or the efficiency, scalability of the graph generator method can play a very important role. Otherwise, the algorithm speed will be very, very slow. And based on this branch, there can be other two minor things. I think maybe we sometimes need to differentiate them. One is called the graph, the edges and nodes are actually co-evolving, meaning that the edges and nodes both have self-driving forces. For example, take the COVID-19 cases where we view each node as a state. So the state have a number of cases and deaths which will evolve as a node features, and the age can be the mobility from pairs of state, but such mobility will not is not totally determined by the node features, right? So essentially, even without COVID-19, such mobility may still exist. So that means that the node and the edges itself are both self-driven and also influenced by each other. And in many other cases where the graph structures in the current papers that we talk about are assumed to be totally determined by the dynamic node features. And this one, I think it is more easy to deal with, because if we want to take into account the smoothness of consecutive graphs among time steps, as Izhou just pointed out, we can just put such constraints among the generated node sequences. But if the graph itself has some self-driving forces, I think maybe it may not be enough that we only put such constraints on the node sequences only. But overall, I think this just at my understanding, because currently I'm dealing with different dynamic graph structure learning problem, and I think these two are two basic ones that I want to distinguish them. And finally, I haven't talked about yet, but currently, if you think about the graph structure learning in our case, we do not assume that this graph will have some kind of harsh constraints, but there are many other graphs like DAGs, especially for Bayesian networks. So these graphs will have some direct constraints, and learning such graph structures are always solved by some optimization-based method. And I found one very interesting paper that I'm currently reading. I just not finished yet because the math behind it, I think it's a little bit too hard for me. I'm just trying to observe it more better. So essentially, it is called DAX with no tiers. It's continuous optimization for structure learning, published in Europe's 2018. So that paper is just trying to, because learning DAX is also it's essentially a combinational optimization problem. So they kind of transform it to a continuous optimization problems and proposed an really efficient way, because it can solve it. If you look at their code, they can solve it very, very fast. And by treating these kind of constraints on these stacks with very interesting math tricks. So I think if we later on have some problems, we want to infer the structures of DAX, we can go back to this paper to look at it. And yeah, that's essentially the different settings of graph structure learning. But overall, currently, because I am dealing with maybe mainly the second category, and I found one thing that is really important in my problem, and also the current design model for different graph generator, is that we must take into consideration both how the graph generator performs on the task performance, for example, node classification accuracy, and also the efficiency or the scalability of it. Otherwise, the model, especially when applying to the dynamic setting, it may not be very practical to use in the end. Yeah, that's probably all that I want to discuss here today. So any comments here?
Thank you. It's very clear, and I like the discussions today. So for the second work, how is the original network used? Is it like just utilized in the very beginning, and then later we just forget about that?
Oh, so for the second one, actually it will not utilize any of the ground truth graph. So essentially what the graph it uses as a kind of the assumed priori that they just perform the KN on the original node input features and constructed such graph and view it as a ground truth one.
So it's completely based on the features.
Yes, so they do not utilize any of the ground truth graph into the learning process.
Okay, so then I guess for this type of approach, the assumption that the node attributes actually provide all the information they want, right?
Yeah, so the edges will not be self-driven, I guess. Yeah.
Right. So in some other cases, in the extreme case, for example, we just forget about all the original features, and we already utilize that to generate some sort of graph, and we wish to utilize the underlying structure to do some node classification, and then this kind of approach will completely fail.
Yeah. Okay, yeah, I guess maybe this is all for today. So yeah, really thanks everyone for the comments and discussion with me. And yeah, I think that's all for today.
Okay, thank you. Bye.
Thank you. Bye.
Bye.